Okay,
Okay.
hello everyone. Hi, thanks for joining in our next Saphir regular webinar. I am very happy to have with us today Freya Blekman. She is a lead researcher at DESY in Germany. She also is part of the CMS collaboration. She also holds a joint appointment, a professorship at the University of Hamburg. She has wide experience in particle physics experiments. She has led multiple physics groups at CERN, mostly focusing on BSM physics using top quarks. And up until recently, she was also responsible for the communication of physics search results by the CMS collaboration. So she's very active in science communication as well. And so I'm very, very happy, Freya, that you accepted our invitation to give us this seminar. Please go ahead.
And now I'm trying to share. Hi, everyone. Thanks, Giovanna, for the invitation. I'm always happy to do these things. So let's see. I hope everybody can see now. No longer see me, but instead see the slides.
Yes.
Exactly.
Yes.
Now let me also fix that a bit so I don't see myself, because otherwise. So let's try again. Right. Okay. So my screen show. I lose my mouse when I do that. There's a big bar in the middle of my speech. We'll get there, people. Okay. So hi, everyone. Indeed, my name is Freya Blekman. I am a member of the CMS collaboration, and when I received these invitations for this seminar, I tried to figure, well, I put a bit of thought on what I wanted to talk about. So, of course, CMS has a really, really broad physics program. So no matter what I choose, it will always be a subsection of what we do. So I cherry-picked, and I will happily admit that. And I picked some stuff that I find interesting or that I think is a very, very hot topic. And but I will gladly answer questions about other topics as well as I can, because I am very well embedded in the CMS physics program and have been for many years. So very likely I will be able to at least at some level answer any questions. So that being said, let's see. Oh yeah. Oh, I'm also very active on social media, so I forgot about my advertisement. You can follow me there. I actually have made by now a tradition that every paper that we put out in CMS, I say why it's important. I give my opinion about it. So you more or less, and I do quite a lot of other science communication there as well, and some outreach. So feel free to join me if you want. So because I understood that this is a seminar group that is quite diverse and not just experimental particle physicists, and also has a lot of students there, I'm really starting from the start. So starting from the start means starting about why we do collider physics. So collider physics we do out of curiosity, and we do it to understand the smallest constituents of matter. And that in general means that we smash things onto each other to see what the constituents are. That is, of course, a very, very simple abbreviation, and this is also why these cavemen look at small rocks. But the essence of this cartoon, I think, is very good, because it reminds us that indeed it answers some of the very, very basic questions, particle physics. What are we made of? How do things stick together? And does that using both very complex mathematics and very complex machines, but in principle the ideas behind them can be rather simple. We use a Large Hadron Collider like a microscope to probe the smaller scales that humanity can probe, and we do that in a very controlled and efficient manner, unlike these cavemen. So what is definitely also true is that these cavemen have a discussion about statistical uncertainties, and I will get to that in a little bit as well. So the scales of the subatomic world are at the subatomic world itself is already at many different scales. The size of an atom is very different than the maximum size, or the size that we know an electron is smaller than. And this also drives particle physics, because over the years, of course, with the more and more knowledge we acquire to develop algorithms, machines, and detectors to detect smaller and smaller particles, we need to do quite a lot of high technology work. But in the end, the goal is indeed to use the Heisenberg uncertainty principle to see how small we can go. And for that, we need large colliders, because we need large momenta. And at the moment, we cannot build high momentum machines that are small. So this is in the end the final reason why we do particle physics. So high momenta, that's colliders, but I also always, my friends in astroparticle physics, they always remind me that compared to space, these energies are tiny anyway. And then I say, yes, but at least we can turn it on and off and control it and look at one-on-one collisions, and we know what we can see. So there is a lot of interaction, particularly with astroparticle physics, of course, including data from our results from our collider, which go back to astroparticle physics and to astrophysics and vice versa, because these fields are linked. In the end, of course, we use the standard model. The standard model is depending on who you speak to, people always say it's a very, very, very successful model. This is, of course, true. We also know that it looks a lot worse if you don't put it on a PR-friendly bug. This is the non-tensor notation. But what it aims to do, of course, is to unify the strong electromagnetic and weak force. And it does that rather successfully, but only up to a certain level. So we already know at that level that there are issues even with the unification of the forces. Because at high, we do not expect them to really, from just a standard model, we cannot really see them unify at high scales. There is, of course, depending on who you speak to, also the argument that in the end we want a theory that also does gravity. I'm very much an experimentalist, so I would say that would be nice, but it's not the end of the world if it's not. But what is definitely true is that we at the moment cannot describe it with the standard model. I would say that's a non-controversial statement. So I already hinted at the fact that the standard model does have some weaknesses. There are some theoretical considerations as far as weaknesses of the standard model. Some of those are up to opinions, such as, say, things like naturalness. Do we really need fine-tuning to be smaller than a certain value, or is that just something that we are attached to? Elegance, do we really need the simplest or most beautiful equations, or do we just should take whatever nature tells us? But I think much more interesting for me, at least, is the fact that there's already experimental evidence as well that the standard model is wrong, and there has been for a while. So just so it's very clear, I've tried to group that here in the 4 different things that the standard model cannot do. So the standard model does not describe the matter composition of the universe, so it can only do essentially matter and neutrinos. It does not describe what dark matter is. It has no dark matter candidate, and it definitely also doesn't know what to do with dark energy. At the same time, the standard model does not describe the actual distribution of the different particles. So by discovering the Higgs particle, we have more or less just moved the question from why do particles have different masses to why are particles interacting differently with the Higgs field. It's not really answered the question that much as far as I'm concerned. So there's no explanation for the underlying structures. There's no explanations for why we have 3 generations. There's no explanations for any of that stuff. So I think this is a very compelling reason to think the standard model is incomplete. Of course, very effective and very successful, but incomplete. The standard model also, and I don't know if you, no, I don't think you can see my mouse. That's a pity. No, you definitely can see my mouse, but I can't change slides. So we definitely can see that all of us are made out of matter, and that means that there's also issues with matter-antimatter asymmetry in the standard model, because the standard model cannot describe the amount of matter we have in the universe. And let's also, of course, the most classical explanation or motivation for physics beyond the standard model is the fact that neutrinos have mass, which the standard model cannot deal with. And just to make it very, very clear, if neutrinos have different masses and they cannot acquire them through the Higgs mechanism as we know it. So that means we need something extra. Either the neutrinos are different or there's extra particles, but there's definitely something extra. And neutrinos, of course, have mass. There's a Nobel Prize for it. This has been measured multiple times. There's beautiful measurements by now. Of course, there's still quite a lot of interesting things being done in that field, but the fact that neutrinos oscillate and have mass is not a controversial statement. So I think with all of those aspects, I think there's a lot of motivation to look for BSM physics, particularly because these machines, like the Large Hadron Collider, can probe many different scales and can still do a lot of other things. For example, they're also great tools for precision physics. And it actually turns out that they are much greater things, tools for precision physics than we originally planned. And you'll see one of the examples from one of these very, very precise measurements later in this talk. So it's also a really, really nice way to study quantum chromodynamics or to do very precise tests of the forces of the standard model. So just to talk a bit more about that, so the way we nowadays think a bit about these things is in some sense, particularly as far as the links between the Higgs mechanism and the evolution of the universe, is that there was at some point an electroweak phase transition where the Higgs mechanism turned on. And before that, all particles had no mass, and after that, they did have mass. And this is sort of this process is, which you can see here in a sort of animation of the bubbles where the sort of Higgs mechanism of the Higgs field is turning on. This is, by the way, also where particle physics and primordial gravitational waves meet. So this is a very interesting subfield. And I predict that in the coming, say, 10 years, these fields are going to get closer together and we're going to start testing each other's theories. And I think that will be really very interesting. So physics with at very small scale that we can see. That's really what the Large Hadron Collider was designed for. This is, by the way, the actual Google front page, the day the Large Hadron Collider turned on in 2008. 5 days after it, we broke it again, so then we could continue working for a year. But Google, of course, was aware there's a lot of particle physicists that work in all sorts of IT sectors, so they had a beautiful page for us. Of course, we don't specifically just look for physics at small scales. We do look for things like dark matter, undiscovered extra particles, new gauge bosons, dark sector particles, and all that sort of stuff. And CMS and Atlas have a very, very large program on that. To give you some ideas as far as the number of papers that these collaborations put out, somewhere between 45 and 50% of these are searches for signatures that are now predicted by the standard model, or where the standard or new particles would create deviations in the standard model. At the same time, many of these are very hypothetical, and I would also say if you actually care about citations, it's not the most cited part of our program. The precision measurements actually, and particularly the QCD and precision flavor physics part actually have a lot more scientific impact in the end. But it's very important to do when we take the data anyway. So the standard model, it's very, very successful, as I already said. I think this summary plot, which is from one of our recent papers, CMS recently had a exercise where we wrote, we were invited by Physics Report, by the journal, to write a number of real review papers. And one of them was focused on standard model precision measurements and cross-section measurements. And this plot is from there. Here's also the reference in the bottom if you want to check it out. It's a long paper, but it's really intended as a review paper to give some idea of what the status quo is at this point for CMS after having started essentially 15 years earlier. And you see that we cover a lot of orders of magnitude, from 10 to the 11th, or maybe 10 to the 5, if you want to say, yeah, the inelastic cross section we don't care so much about, all the way to 10 to the -5 in picobards. So that means we cover 9 orders of magnitude. It's really there's a huge number of different kinds of things that you can do with a collider. And as I always tell my students, each of these points is at least somebody's PhD and is likely a paper. So this is there's a lot of work that is compressed into this plot. What I think you should appreciate on this plot is the fact that that the standard model is actually pretty good, as we were already talking about. So the gray predictions are there from theory, and then these are all rate predictions. So this is the frequency with which each particle is produced, and that is on the y-axis, and the theory prediction of the production probability in proton, antiproton, or in proton-proton collisions. Sorry, my Devatron backward. Proton-proton collisions. So that and then compare that to the standard model prediction. And what you will see is that there are some deviations, of course, which is to be expected, but you see that all the very frequent processes are very precisely modeled, and only when you get to the very rare decays, things get a bit more complex and more difficult as well, both to compare and to predict. And you also see that there's still processes that we very much are looking for, like, for example, di-Higgs production, which is related to directly measuring the standard model Higgs, or Brown layer Higgs field, and we hope to see in the coming years. So you see we're getting close there. I said a lot of different things, a lot of precision physics, a lot of orders of magnitude. The other thing which I want to say before we sort of get to the nitty-gritty of the physics is that the LHC is only just getting started. I think this is important to be aware of. So very often people say, yeah, the LHC, what have we heard from them? But the problem is the LHC data comes exponentially. So if you take a look at which LHC runs, we are currently about halfway in run 3. There's quite a lot of data that we have not collected yet, and there's a lot of physics we can still do, and there's also still, so I am very interested in looking at signatures that we just could not look at up to now, and so there's still quite a lot of things to be explored. But it's also, of course, true that the very, very extreme sort of classical signatures that people thought that we would see the new physics in, there was nothing there, at least up to now. But I think it's also very important to know that there's really quite a lot of signatures that we have not looked yet, and some of these are only starting to become available now, just because they're more difficult to analyze, or because you need a lot more data to do it carefully. So that being said, remember the pie chart. We're in run 3. We have about 9% of the LHC data. Most of the results that you will see in this talk, actually all of the results you will see in this talk are all taken with either run 2 or even with very, very small fractions of run 2, because for many of the precision results, you actually don't need the full data set. So it depends very much on what you're trying to do, whether you need a lot of data or you need very, very little but very well understood data. And all of these, this still depends very much on what you're trying to do. So this means that there's still very good reasons for results to come out using data that was sometimes collected 10 years earlier, because the level of understanding of the data is so much more important there. Well, on the other hand, probably if you want to do a quick and dirty bump hunt, you will want to have the most data that you can get. So here is a plot of the performance over the years. So the LHC every year has gotten more and more intense. So what that means is that because of this exponential growth of the amount of data that we get, and that means that when the LHC collides, we don't get one collision in the detectors anymore. So by now, you see here on the x-axis number of interaction per bunch crossing. So every time the LHC beams cross in our detector, we in 2023 got on average about 60 collisions per bunch crossing. So, and out of those 60, probably only 1 or maybe sometimes 2 are interesting. or at least are likely to be very hard scatter events, inelastic scattering events. So that brings us a problem, because of course disentangling all this overlapping information makes it more and more difficult. Well, at the same time, some of our detectors are of course also damaged by this amount of radiation, so they also start working less and less and less. And this is, for example, the reason why for high luminosity LHC we are really improving and upgrading our detectors. So we throw away most of this data, and I think this is important to be aware of. This is driven both by the processing power of our computing farms, but also by things like the fact that we just do not have the capacity or the money to store them. We can just not afford the disk space to save all this data. So at 40 or 30 million collisions per second, with overlapping pileup events, we actually would not be able to save events, because we would be producing terabytes per minute. So instead, we now, it's classical, the solution to that, I would say, at the general purpose detector, so this is the same for Atlas and CMS, is that we use an online selection system called triggers. And here you actually see a projection, how we separate the trigger bandwidth in CMS in 2022. So what that means is, with the total number of hertzes that we had, was in the order of, say, 1200, I think. And here you see which group used how many hertz. And you see that certain groups, like the Higgs group, used a large fraction of these events, but only requested quite a few, and the rest they got from the other groups. Because, like, for example, the top physics group mostly uses signatures that have top quarks in them. The standard model group and the Exotica group, again, they request very different signatures. So this means that the different signatures are typically shared between physics groups. So you can do different things with them, because as you can see, these blue bars are definitely not the same as the green bars, which is what the group probably says would be the core of their physics program. But it also means that tough decisions need to be made, because there's a maximum number of hertzes, and people don't necessarily get all the bandwidth they want. And that is why I want to talk a bit more about triggers and about CMS trigger and parking and scouting strategies, which is another paper that we recently published, and part of this series of overview papers. So CMS has been pushing for a while already since run 2 to diversify our data tracking strategy and not just rely on this classical normal trigger strategy. And so you see that we normally have a stepwise selection, where we first have a level 1 trigger. So this is a hardware trigger that uses FPGAs and things like that to make very fast decision on whether a collision is interesting. And then we are left with about 100,000 collisions per second that we actually look at in quite a lot of detail. Actually, not exactly the same detail as we would do in a real analysis, but we have enough detail to really make to have physics information there. And then in the end, out of those 100,000, we originally could only save 1 or maybe 2,000 events per second. So we already during run 2 started to save events using other streams, mostly using the same method as before, but with parking, where the idea was that we would save the raw data, but we would not pass it through the full reconstruction code, so it would not be available straight away, like our normal data is available after about 2 weeks. But instead, it would only get available when there was time to actually run the computer, sometimes a year later. And at the same time, we also introduced a scouting program. And this is what I will mostly talk about, which instead of making the choice that we save every event and all the information, instead, we already do a bit of the analysis on trigger level and then actually save the sort of the analysis level information of the events, not just the raw data. And this makes the events a lot smaller. And that means we can save a lot more events, because in the end, the discussion is not necessarily about the number of events that's driving these decisions. It's really about the number of gigabytes. And so if you can make each collision smaller, that means you can save more collisions. So these are very, very complex collisions. Here is one. There's another one. So this already gives you some idea. This is a digest event. And here you see a Higgs event, actually. You see all these additional tracks and all this information. So it's very important when you do that, particularly on trigger level, that you also save the right information. Because unlike the offline system where we just save everything and then you run whatever fancy algorithms you sometimes develop years later, here a lot of the algorithms are already run in the trigger system. And you need to make decisions there, and you need to make sure that those decisions are high enough quality. So this involves watching the data much closer and much earlier as well. So as I said, there's this overview paper. It's recently been accepted by Physics Report. It's long. I will not do it justice. I think particularly if you're a phenomenologist who has been told by experimental particle physicists that your signature is invisible because we throw it away in the trigger, it's definitely worthwhile checking out this paper to see if we could do it now. I think there's also a lot of potential for standard model measurements that we are not really taking full advantage yet. So I believe that just like the LHCb collaboration already did, that this is the future, and we'll really move to a paradigm where this is the norm and not the full raw event saving. So as I said, the LHC bunch crossing could be 40 megahertz, but it's really 30 megahertz because there are some empty bunches because of the way the beam dynamics works. And the idea is to then reduce that trigger cross-section to about 1 kilohertz. There is a bottleneck. We can use scouting for delayed reconstruction. And we actually, in 2018, already had this scouting data that we got 10 billion extra events that we did not save any other way. And this is what we call parking, and what Atlas calls delayed reconstruction. There also is, as I said, scouting, and this really greatly reduces the event size. So I already hinted at that when I was discussing this infographic before, but the event size really goes from 10 kilobytes when you started out with a raw event that is 1 megabyte. So you really have a factor 100 more space, just because your events are a factor 100 smaller. This is also done by LHCb, and at High Luminosity LHC, their plan is to do that 100% of the time. And we'll see how close we will get to that, because there will always be precision measurements where we probably cannot use this. But I think it definitely has a lot of potential. No, that's the wrong way. So what can you do with this object? So here are some examples of things that we could not do with our standard reconstruction, not even when the LHC started. So we can really go to much lower momentum thresholds, particularly for, say, dilepton systems. So, and that opens up a flavor physics program a la LHCb, and I hope our LHCb colleagues will be happy that we will start competing with them. But this is definitely one of the main goals of the scouting program, was to also have more flavor physics potential in CMS. So here on the left, for example, you can see the dielectron invariant mass spectrum between 2 and 11 GeV. So this is not something that you would expect to be able to observe in this much detail at a Hadron collider that's colliding at 13.6 TeV. And you see the very clear J psi and psi and the epsilons there. Of course, this is electrons. Electrons are difficult, but the fact that you can see this means that you can do physics with them. That's pretty clear. Because this is what the trigger analysis does. In principle, this means an offline analysis will do better with these even after that. But it's already very, very impressive. The same thing here, for example, you see for the dimuons, where there's already other much more precise results coming out. CMS is not called CMS for nothing, compact muon solenoid. We're very good at muon reconstruction. And intrinsically, the detector should be able to reconstruct any muon above a momentum of, say, about 3-ish GeV, unless you don't want to use the muon system, then you can go even lower. And here you see the actual resolution of the resonance width as a function of the resonance mass. So you see that the resolution is flat as a function of mass. So we really are already in the regime here with the scouting objects that we essentially have a flat resolution and can really do physics with it. So there's real physics results already coming out of that. So here's some examples of that. So there is a rare decay of the eta particle to form muons, which came out very recently, and it uses the run-2 scouting. At that time, we were only saving muon events, so we were only saving muon information as well in the scouting. So this is by now different. By now we have the full event information, so we can really do practically everything that we would do in an offline analysis as well. And you see that you have this beautiful peak there, and you can also see the mass of the eta. It's very, very low mass, so you can already imagine these muons do not have a lot of momentum. It's really a very difficult analysis, and it would also be very difficult to select these with a traditional trigger, just because you cannot save. There will be a lot of background, and it's really quite hard work to actually isolate these if you would not just be able to save any muon, and that's what we did here. So there's also an example here is, for example, on the right is the quality or the effectiveness of having triggers for hadronic activity. So the LHC is, of course, really a hadron collider. And typically, when we have events with just jet signatures, we can, of course, we trigger quite effectively on things like electrons and muons, and particularly if they're isolated and above, say, 50 GeV or even 40 GeV, they will definitely be saved. But this is definitely not true for quarks and hadrons and gluons, so for jets. So here you see in red and in black the turn-on curve, so the actual trigger efficiency for our triggers that were running in 2022. So you see that the standard HT trigger, because of rate constraints, so this is the red curve, we can only save events where the total hadronic energy of the events was above, say, 1,000, 1,100 GeV. So anything below that we would just not save. It would just be thrown away. But at the same time, the scouting actually can go down to 300, 400. So this is much, much more. There's this whole range of extra physics objects and extra physics interest that you get through scouting, which is really quite exciting. So this also is true for things like dijets. One might say dijet events, in principle, they're like I said, they're some of the classic signatures of physics. They're also very, very important for precision QCD measurements, to actually measure them in the full phase space, because you can do deep and elastic scattering measurements, particle density functions, all that sort of stuff you do with dijets. And if you only can save dijet events with invariant mass of above 1 TeV, and that's what you see on the right plot, which is the classical selection plot, you lose a lot of data. And that really means also losing a lot of physics. While in the right plot, yeah, they look very similar, but that's because the x-axis ranges are different. So read the x-axis labels here. The triggers there are turned on at about 200 GeV, so there's a lot more dijet events that you can study there, and this will enrich the QCD and precision standard model program there as well in the future. So just an example what you can do in a BSM search. So here is an example of a Z prime to dijet search. So this is looking for an additional peak in the invariant mass spectrum of dijets, coming from some sort of Z prime like particle. Can also be some sort of gluon connected to extra dimension models, all this sort of stuff, that all would create extra resonances in the dijet invariant mass spectrum. And here you can see on the y-axis the coupling, so the sensitivity of the search, and then on the x-axis you can see the invariant mass that we probe. And we can see that there's different ways to do this. So if you go to very low mass, actually what you do is you use very high momentum jets, and you actually treat everything in the jet as an event and actually look at what's happening inside there. So you have all these boosted results there, but that at the same time, you have with scouting, you can really be competitive. And there's even areas that we could not probe previously that we are now orders of magnitude sometimes better than we were before, just with the scouting, because we're in this sort of few hundred GeV to 1 TeV range where it was very, very difficult to access. So there's real gains for physics doing that. There's also, if you are really into exotic stuff, there's long-lived signatures. So this has been a BSM signature that has come in fashion in the last, say, 5 to 10 years. I guess I should be happy to say that I was ahead of the curve. So the first long-lived particle I did is about 10 years ago. A paper, and we didn't see any, but I think it's also experimentally, these are very, very interesting signatures because you really use your detector in a much more creative way than you would normally do so. And I think that's important as well. And these are unexplored signatures. They are very well motivated by physics, particularly by all sorts of dark matter and dark sector models, which predict extra long-lived particles, which would travel a bit through the detector before they would actually start creating standard model particles. And that would mean they would not be produced at the center of CMS. And we are actually now really set up here. You also see some scouting objects from that, and you see, and they're actually here, there are multiple histograms in this plot, each of them with different collected at different distance from the detector. So you have particles that are really produced at the center. So those are the blue and orange ones. But then once you go to red, these are particles that are already being produced in the active detector volume, so where the where the pixel detector is. And you see, you can still see all the standard model particles. Again, this is also a result, so you don't see anything extra, and that means that at least at these distances, we in muons, we don't really see that much extra, any extra physics, I would say. Of course, within the statistical uncertainties, because you see also that when you go to, say, 7 centimeters to 11 centimeters from the collision point, by then we are actually, even with this large run-to data set, we are still statistics dominated. So there's a lot of things. LOMA, another very good example is neutrinos. So we were all talking about the fact that we need extra neutrinos, or at least some BSM, to explain the neutrino oscillations, or the fact that neutrinos have mass. One of these are extra neutrinos, have Majorana neutrinos. So those are also done by scouting. And because this is particularly good for very low mass signatures. And we did that. We've done already things like Higgs particles decaying to BSM particles that then decay to other particles that we can see, where the BSM particles are long-lived. And these results are also coming out recently. Yeah? So this is a result from from last month. Another example of a very nice standard model measurement result, which I think is very representative of what you can expect to come from CMS in the very near future, or in the coming years at least. So this is a precision flavor physics result where we actually measured the branching ratio of the D0 to 2 muons. To 2.6 by 10 to the -9, which is the world's most competitive measurement. Obviously, we don't see anything yet, so this was a limit. Here you can also see the little plot of where we should see something, and with the prediction, we're still an order of magnitude off, but or two. Well, but nobody has measured this precisely. Also, not the precision flavor experiments, which is important to be aware. So this really makes CMS essentially competitive in the flavor sector.
Excuse me?
Yeah?
Can you go back to the Higgs portal, the previous slide?
Yes.
Yes, there are there searches for this type of processes, but without the Higgs not being on shell, like because I guess that this is part of the
Yeah, indeed, this one requires that the Higgs actually is on shell. So because the 125 GeV will really help to reduce your background. These kind of searches can be done with the scouting data. They're not out yet, but yes, there's a lot of things in the pipeline. But that's more difficult.
So it's more difficult, but I didn't understand. There are some searches.
It's possible, but it's not out yet.
Ah, okay. Okay, and Atlas Atlas hasn't done that type of search. Neither?
As far as I know, not yet. This is a difficult signature, particularly once you add the displacement. These are very low momentum particles by that point. So you need 4 fermions. You need them to both independently already create an invariant mass. So this is more or less how you do background rejection.
Mm-hmm.
It's almost a Dalit style analysis, and then you require the Higgs mass on top of that. But in principle, it would not be that much extra to also do this for other Higgs masses. I recommend you look at the paper.
Okay, thank you.
So there's also quite a lot of happening when these particle collisions are getting more and more complicated, and that means that we also do a lot more machine learning than we did at the start. So I should check how I'm doing in time. Yeah, I like to talk. I'm going too slow, so I'll speed up. Sorry. So I'm going to give you one example from something I work on because it ticks many boxes in machine learning and because I think it's interesting. The example I will give is 4-top physics. So this is simultaneous production of 4 top quarks at the same time. Very relevant in the context of both BSM sensitivity and the standard model. Has sensitivity to the Higgs coupling and the top Higgs coupling and to extra Higgs interactions, including anomalous coupling. So it's very, very interesting to do. Typically, it's done only in the lepton signatures. I will show you some other results later in the talk from the leptonic signatures. But CMS can now also do this result in the signatures with much more jets. For example, the all-hadronic signature. So these are events where, well, in principle, if you have 4 top quarks, you should expect 12 jets, but we don't always have 12 jets. Sometimes we miss one or they overlap. So it's at least 9 jets, and then we split it up and categorize it further. This relies very heavy on machine learning for isolating both requiring the presence that there is a top quark and requiring the presence that there are B jets. So there's quite a lot of innovation there, and the B-taggers are really leagues better by now than they were at the start of the LHC data taking. But this analysis also uses machine learning for categorizing the background and for sort of separating the signal and background. And again, that's not by now also the norm for the LHC, but what this analysis does special is that it also does the background prediction using machine learning, and that's quite special. So what it does is it actually, this analysis uses an autoregressive flow neural network that will is trained to transfer distributions according to the information in the event, to transfer distributions from a control region to the signal region. And that way you can actually use data for the background and which is, if you know these kind of analysis, this is actually one of the big challenges, is the background prediction of this blue background. Because to have QCD, both to generate enough events to do that and to have them at the is difficult / impossible computationally, but also the QCD event generators, QCD 12 or 11 jet events are just very, very difficult as far as QCD theory. So they're also not particularly realistic. So this way we get the data, which of course has all orders and those other things, and then we use the neural net to transfer from one to the other. You can also see from the data that it works quite nicely to predict this background from this control region. So here you see also a plot from one of the 2016 yellow reports, or I think 2018, which shows you how we expected four-top production to improve as a function of integrated luminosity, using some of the leptonic analysis from CMS, where we just more or less redid the analysis, but with more simulation, with higher luminosity to predict how well we do. And we actually thought that if we would just continue doing exactly the same thing we were doing before, that we would never reach 5 sigma, and with systematic uncertainties, we wouldn't really we would never even have a probability of seeing it if the systematic uncertainties that we had were realistic. And that's, of course, well, a very good motivator for people to get more creative, because, of course, here you see a recent summary plot. We actually see these both Atlas and CMS see four-top production at 5 sigma in the multi-lepton final states. And the reason that was done is actually a lot of these analyses were redone. And here's the CMS version of these analyses. So this is the multi-lepton. So 2 same charge leptons or 3 or more leptons. And then you do a lot of neural networks on top of that to combine the hadronic activity and to really train to disentangle between the different backgrounds and the signal. And just by reanalyzing the same data, and this is really the same data, in very, very late 2018, straight after data taking. So this was one of the first analysis we did when the run 2 ended, to what we can do, 6 years later. You can see that we can go from essentially 2.7 sigma expected to over 5 sigma expected, let alone observed, but expected. So we really have, with the same data set, with just smarter machine learning and smarter analysis techniques, better B-tagging, we can do so much better already. So waiting and having this data under control really helps. So this is a particularly interesting channel also because both Atlas and CMS see extra tops in four-tops in all final states. And also these tops are sort of consistent with 3 tops. But this is very difficult to say if you're just doing if you're just counting leptons, or if you have a neural network that's trained to identify 4 tops to really say that you see 3 tops. But what is clear is that the cross sections that we see and the extra events that we see on top of that could be consistent with 3 tops. And this is the way these analyses are going. So these are all in preparation, I'm sure also in Atlas, but definitely in CMS, to separate this in a more careful way and to really carefully examine this in run 3. So as somebody who has been doing machine learning at a Hadron Collider since 2000, I do have some thoughts on this, because these collider analyses are by now so heavy of machine learning, and that I think it's important and prudent to say, are we certain that we're not just teaching our machine learning how to identify a math graph for top events instead of the real data? And that's the reason why you see extra events. So, and this I think is something that will also come in the near future, where the machine learning is getting smarter to deal with this in different ways. So last but not least, in the last, say, few minutes, I'm going to talk about the W boson mass, a very recent result. I think it's important to at least discuss it, just so everybody is aware. Here, setting the scene. So this is a result from the GFitter group, which is one of those teams that does the standard model fit. So what you do is you take the standard model, you put everything in except for one particle, and then you see how well the standard model can predict your measurement. And when you predict the W mass, the predictions from the standard model were really not so great, and particularly already, well, but within error bars, just because the position was what it is. But then the CDF result, of course, appeared a few years ago, which measured a completely different W mass value. And then people got very excited. Now, to be fair, considering that all the other results were consistent and only CDF was not consistent, I was already not particularly excited, but some other people were. So, and it's a very important thing to measure. So we have And CMS has taken a while to really design a very, very robust W boson mass measurement analysis, which I will not do justice. It was very long time in the making. There's a very nice result from Josh Ben-David, who gave a certain seminar about this, including a webcast that is available. There is by now the preprint, as in the physics summary, so the preliminary result is available. If you are a theorist that works on this stuff and you're missing information in the paper, I would say complain about this now, not when it goes to the archive, because we're now deciding what plots to put in this paper and also what additional information to include. So the essence of this paper is that it does not rely so much on extrapolation from the Z boson to the W boson. This is important. There were also some other things that were involved. There were lots of experimental improvements. So we took very, very well understood data from 2016, really improved on both the tracking, made new tracking algorithms. We needed to know our magnetic field even preciser. It's lots of theory development was needed to do this measurement as well. It's a tour de force. Uses the cutting edge of everything that we have at the LHC. So to summarize it on one slide, you take very, very, very precisely well understood single muons events. We do not do an electron channel because the electron channel comes with other backgrounds. And we have enough muon events, so there's no need for statistics reasons to do that. We then directly measure the PT and pseudo-rapidity distribution per muon. So we do not measure an invariant mass peak, like what was done by Atlas and also by CDF. And then we actually use also check that the helicity behavior is consistent in a statistically less sensitive but valuable check, and it's consistent. And we get all of the information as far as the muons we get from JAPE size, which we can reconstruct already, and get all the cross checks from there and test all the performance of the muons with JAPE size. And that means that we can use the Z to really do a full cross check to see if the Z boson is consistent before we unblind it. And we did. And yes, of course, when we were doing this, this is a long term, and this was really needed. There were times where we were at the first time, of course, not at where we expected for the Z boson, and that's why you do this kind of thing. So it relies on very accurate theory predictions as well, of course, because you need to, to actually predict the muon PT and eta spectrum, you need to have precise theory. So here you see what goes into the fit. So this is a very, very precise fit with lots of bins. Each of these is one bin, and we've sort of grouped all the momentum and eta. So each of these little distributions is an eta distribution and a bin in PT. So you sort of are scanning eta in PT if you look at it here. For positive muons on the top and for negative muons at the bottom. So you see actually from the PDF that there's a difference in momentum spectrum already at that point. And this is the pre-fit. So before we do the statistical fitting to actually constrain all the systematic uncertainties, this is how well the data agrees. And then if you fit afterwards, and after 10 years worth of hard work, you get this result. And you see from the agreement how precisely this agrees. And that you can then use to actually compare and to really test different W boson mass hypotheses that all create a slightly different PT spectrum. And from that, we get our W boson mass measurements that has this uncertainty of 9.9 MeV, which is really highly competitive. The larger systematic uncertainties are in that case are things like the muon momentum. Of course, if you want to measure the muon momentum precisely, it will be an important effect. But also, for example, this small non-prompt background that we have, and actually the size of our Monte Carlo samples. So the fact that our simulation is limited, it's again by CPU resources, and this uncertainty is not negligible. On the theory side, there's of course also uncertainties. And this result, as you can see how competitive this is from this summary plot compared to previous results. And I would also say that even if you did believe the result by CDF, I think it's very important to understand what went wrong there, but it's very clear that the result is definitely not consistent with the other results and should not be used as an argument that the W mass is this far off, because it's pretty clear everybody else is consistent. So to conclude, CMS, it's a very diverse program. We do a lot of different things. We are by now moving towards using scouting and parking, so we can do even more. That means on-demand triggers, lower thresholds. Ideas are welcome. A lot of this is software-driven, meaning that if you can convince somebody on CMS to type this into the trigger, it is available. And machine learning is really pushing the edge, and this classical machine learning is, we need to get smarter than that in certain cases. It's also getting more innovative in things that you normally did not use machine learning for. And of course, we've measured the W mass. So thank you for the invitation and for listening. And I'm sure there's many more questions still. And also it's getting slowly dark here in Hamburg. So I'll turn my light off so you can see.
Thank you, Freya, so much for this very comprehensive talk. And congratulations on the CMS measurement on the W mass. The uncertainty looks as small as CDF, so that's pretty impressive to see, and I wanted to highlight that.
Yeah, we cannot claim it's the smallest one because they're actually smaller. So, but it's definitely small. This I would agree with.
Very small, yes. Thank you. Are there any questions, more questions for Freya? I can start. So I've always had issues with this scouting, like trigger philosophy. And just so that I understood it correctly, basically there is a trade-off, right? You are aiming for higher rates in compromise of the full event reconstruction. This is the philosophy.
Yeah, this is the philosophy, but let's also be fair. So the CMS high-level trigger runs exactly the same software as our offline reconstruction.
Okay.
So this is, I think this is I did not emphasize that here, but this is why we can do this so effectively. It would be very different if there would be completely custom triggering. So things like the fancy B tagging that we have nowadays, that can just run on the high-level trigger. The only thing, of course, is in the end, you do not save the individual hits anymore. So if you want to write a completely new reconstruction algorithm, you have a problem. Because we do not save the hits. We save the tracks, and we save the jets, and we save the leptons, and maybe some information around it, but we will not save every raw electronic deposit anywhere in the event anymore. You already effectively get almost 4 vectors out.
So there is still a decision to understand what are the triggers that will define these data sets. So this is something that comes later on.
I don't understand the question. So, but in principle, there are technically triggers running, but the thresholds are just so low that it doesn't matter.
Okay, so this is my question. So, for example, you can have a scouted, I don't know if that's a word, scouted data set for like muons, for example.
Yes, but you can also have a scout, but we now also have missing ET in there. And
and jets as well.
And in the same event. So you can have a TT bar event where you have 1 muon, 4 jets, of which 2 are B tagged, and missing energy. That you can have that. So
but
it's
with
not
low
that you
thresholds. But
with low thresholds on all the jets. So the jet reconstruction can go down very, very low. The leptons can go down to very low. So all these events, you will just save a lot more events that you normally would throw away because you're near the threshold. Yeah.
I understand, but the difference with the parking then, so for example, for the parking, it's like data waiting to be fully reconstructed, and then you also get enriched samples with low threshold hadronic activity.
Yeah, you have a different trigger suite. So there, what you do is you carefully select your triggers to be events that you find interesting that you normally would throw away, but you take the full event. So for example, for the next W mass, parking would be a very good example as well.
Okay, I've seen one analysis for LLPs with HNLs with BB bar events that really was very impressive to see how low in mass you could reconstruct this long-lived part. So I was wondering which other types of, so for example, for displaced triggers, all these strategies are going to be very beneficial for that, right?
Yeah, but so here, this is why I would emphasize it. So we started out with muons. And muons, we were already doing this in run 2. But now we have electrons, we have jets, we have beat tagging, we have missing ET, we have it all in run 3. So there will be results coming out eventually that are doing a TT bar cross section with scouting, yeah, or Higgs for muons, or well, Higgs to for muons might become now so precise that you don't want it. I don't know. Maybe Higgs to BB bar might be a good one. That would be, or VBF. We have VBF signatures, all of that we have in there. So we can, in principle, do anything you can do with an analysis where it probably doesn't, where you don't need your objects to be the highest efficiency, but you just need to have the data on tape. You can do with scouting. And the goal is indeed to, well, yeah, it's very similar to talk of it in sort of Atlas versus CMS discussion. There are, in Atlas, I'm sure you guys have a rule of thumb that a certain fraction of analysis uses the standard AOD or mini AOD or nano AOD. I forgot what you guys call it, sort of the group entable. And there's a certain fraction of analysis that cannot because they need dedicated reconstruction. We have essentially moved that full decision to the trigger. And if you can use the standard entable, you can use the scouting. And you get a lot of lower thresholds. Yeah.
Excellent.
Yeah.
Thank you. Questions? More comments?
I hope it was clear. Easy questions are allowed too. Don't worry.
Yes, please. Students. I see many students connected as well. You mentioned that LHCb also it's implementing scouting widely, right?
LHCb, it's part of their standard strategy for run 4. So they will do this as well. Yeah. I'm trying to see where's my slide where it was explaining this. No. Yeah. So LHCb, to be fair, like I said, so the only thing that's novel about scouting in some sense is the fact that we gave it a sexy name. So that's maybe a bit too humble, but the idea, it's not our idea. Having this trigger level analysis is in principle how, of course, a lot of other experiments already work. It's just that it was not very common at Hadron colliders because it was not technically possible before, because the software that had to make this very, very fast decision making was just not good enough at the Tevatron. So we had custom triggers. Like I can tell you, I was on the D0 experiment. The D0 trigger software was even on a completely different computing platform than what we did on analysis, because it ran Windows while our offline analysis was on Linux. So this was completely different. So it was just impossible before, because you had to make this very, very fast decision, and then the data was gone after you made the decision. And now that we have, most of the software is pseudo identical in the trigger, why not? Like I said, 80% of the people they use standard electrons and standard muons and standard jets. What they have in the trigger is fine.
So hopefully we will see many more results for display stuff, which is what I would be interested in.
Yes, no, definitely. Display stuff is also one of my interests, so it's happening. Like I said, the electron peak that you saw at low mass electrons, that also works for displaced electrons, for example.
Yeah. Also, let me try to comment, because you mentioned this machine learning trend of all the analysis, but I saw on your slide a comment on reinterpretability of the results. What you mean is that it's hard to do if people don't publish the likelihoods.
No, but even with the likelihood.
Even with the likelihood.
Even with the likelihood. So let's just say if you unless you can pass your full, you also give the actual neural network a four-top analysis where you pass a BSM model. I actually wrote a paper about that in 2015 or something like that. So this has been known that it was going to happen, but I think we're now really very close to it. That once the physics signatures of a BSM signal becomes very different from the standard model signature, you cannot use the standard model signature or the standard model analysis of an analysis that was trained on the standard model to see, you measure this cross-section number, so I can exclude my BSM model with that. That's eventually, you're gonna hit edges there where you cannot do that anymore. And that means that we are gonna think that we've excluded things because of the simplistic interpretations that are not excluded. And that I think is very important to be aware of, because that means we're being more conservative than we really, than our data really is. And I think a very good example is this 3 tops. I do not think there is extra 3 tops, just so it's very clear. Of course, we're going to measure it, but I think this is a higher order effect that we just did not have in our simulation in some way.
I see. So
that's an opinion, just so it's very clear as I'm being recorded.
No,
I can't
no.
prove that. Yeah.
Of course, but I think it's very nice to highlight that there is also an opportunity in this direction as well to think about how to best send information also for help your theories friends.
Yeah, totally.
Thank you. Okay.
I have a question.
Yes, please,
Maybe it's
Bastian.
a basic question. Could you say something about the non-pointing photon searches in CMS, or if you have some?
I don't have slides, but I can tell you. So, but I am familiar with the searches. So the non-pointing photon searches in CMS. I don't know when the most recent one was. It's been a while because they were already completed for run 2. They all rely not on just on, well, of course, for CMS we can't decide from the calorimeter information whether a photon is pointing. So instead we use the actual timing in the calorimeter because it's a crystal scintillator calorimeter. So it's the timing resolution is very good. So we actually just see if a photon arrives slightly too late, and then we conclude from that it's non-pointing because it must have taken a longer route. So these kind of techniques exist and have been published. Now, do you have a specific question about a specific non-photon?
Actually, well, I know a paper, but from Atlas, in which they looked for neutralinos as long-lived particles, and then the neutralinos produced in pairs, and then decay, each of them decaying into a photon plus a gravitino, which is basically missing transverse energy.
Yes.
But at least what I saw in the Atlas paper is that the condition for this missing energy, it must to be above 75 GeVs, which maybe I'm wrong, but I tend to translate that into the fact that the mass difference between the neutralino and the gravitino should be at least that difference, I guess. So
indeed. So the whole idea is when you have, indeed, if the mass differences get smaller, you get softer events typically.
Okay.
Or at least things are less on shell, and it will look much more standard model like. And I think your confusion may also be because of the fact that in CMS these kind of signatures are classified as exotica, not as SUSY.
Exotic.
Yeah.
Okay.
Yeah. So there are results like that. They might not have been interpreted in exactly the same model, but most of these results, they just count number of displaced electrons and they see 0. And I don't think there's any result that does both displaced photons. But I don't think there's a result with displaced photons and missing energy. But that's not necessarily a problem. In principle, as long as you don't cut on it, that's fine.
Okay.
Yeah. So
So
check.
dark photon to dye muons, I think CMS has published some
Yeah.
displays, dark photon decay to displace muons. This is the
Dark photons. Yeah,
dark
definitely.
photons, yes.
But also just a photon that is the actual standard model photon is displaced. So a long-lived particle decaying to something, decaying to.
I see.
So we have results, and the results use the calorimeter timing. That's our trick, because we can't point. Atlas has a much nicer electromagnetic calorimeter where you can see the full cluster and they can really point, I assume. And we have this crystal calorimeter, which is very good for energy resolution. So it's fantastic for Higgs to gamma gamma and things like that. But at the same time, of course, this it cannot do. So you have to be smarter and do something else. Yeah.
I see.
Thank you.
Thank you. Okay, I think we are a bit past on time. So in honor of that, thank you, Freya, so much again for your nice talk. And thank everybody for joining us.
Yeah, thanks. And I wish you all a nice afternoon.
Thank you. Thank you. You have a good night.
Yeah.
Ciao.
Bye.
Thank you.
Bye,
Thank you.
everybody.
Bye,
Thank
everybody.
you.
Bye, thanks.